Okay. So module 5, big picture. Here's what I'm thinking. Well, we call it, okay, sorry, getting ahead of myself. We call it further topics and functions. Let me see if I can get that written. Oh, no, I can't. It's not spelled that way. Okay, further topics and functions. Almost there. What that means is this is not a particular topic that we're covering. I guess the idea is that with this module, we've talked about polynomial functions and rational functions, and now right before we change gears, I guess, and going into module 6, changing gears into a whole other world, we're going to talk about some last things that we just, we couldn't categorize real well as a whole module, but there are topics that are worth bringing up that are relevant to functions. And I guess we're not really abandoning the idea of functions entirely as we go into module 6 and beyond, but we are, I guess, rounding out the idea of what we call algebraic functions. And we're going to be looking at weirder ones, transcendental functions, and some other topics too. So all that to say, further topics and functions really has kind of 3 big ideas in it, and so here are the 3 big ideas. One of them would be composition of functions. We call it composition of functions. Composition, we'll talk about that. The second one is we call it inverse functions, or inverses of functions, or something like that. So we'll just say inverse functions, because the functions, the inverses we'll be talking about are also functions themselves, of course. So whatever. Inverse of a function is a function. And then, although, well, whatever, let's say about that. And then finally, part 3, we'll just call it other algebraic functions. And we'll talk about what that means when they say algebraic functions versus other kinds of functions and stuff. I'll give you some kind of an intuition about that. Okay. Anyway, here's the big 3, and so we'll try and be quick about these best that we can. So for composition, let's talk composition first. Composition is the idea of taking 2 different functions that do their own thing, that have their own inputs and outputs, just like a machine has, like we're always likening it to some kind of a machine, and kind of wrenching them together, tooling them together so that they do the job of 2 machines as one machine. And so I guess it would be like, so composition could be like, suppose we had a machine, okay, machine 1 or whatever. And you say, okay, machine number 1, you found your mad scientist into, or, he's a mad scientist neighbor, but at least he's doing good things for the world, I guess. And so whatever, he's taking rocks into chocolate, he's stealing your landscape rocks to do it, whatever. That's machine number 1. And then your mad scientist other neighbor or whatever, machine number 2, you had another mad scientist neighbor on the other side of you. He has a machine that he made that, incidentally, without even knowing the other guy, or maybe they're mad scientist brothers, I don't know, but without it, we'll say they don't know each other. I don't know. He has a machine that he made, and it turns chocolate. It takes chocolate. How do you spell chocolate there? It takes chocolate. Nope, messed it up again. And turns it into like gold, and you're like, that's even cooler. The first machine was rad, but then this machine knocks it out of the park, And so you're looking and you're like, machine 1, machine 2, rocks, chocolate, gold, And so you're like, well, I'm noticing here is that, well, okay, the inputs of one machine, okay, then it spits these things out. And I'm noticing this though. Okay, input is a rock, output is chocolate in this machine, And then that same output becomes an input into another machine. That same chocolate could be an input that then becomes an output of gold. And so you're thinking like, well, couldn't I just, if there were just a way that I could just be a little bit faster, if I could somehow, like, again, kind of wrench these 2 machines together so that they do all that job just as one, because right now I could turn rocks into gold, but I got to run it through 2 machines. And so I guess function composition would be the idea about taking these 2 machines together and just using one machine to turn those rocks straight into gold. You know, not that chocolate was bad, but you know, gold buys you a lot of chocolate, and you can choose the kind of chocolate you want. Obviously, gold is a hotter commodity, and so this would be function composition. Composition would be taking two machines that do two jobs that are related, and then running them together so that they can do both of those jobs real quick and get the jobs, two jobs done at once is kind of what's going on. And so here's kind of what it looks like when we do function composition. What if I took, okay, let's say take f of x, and we'll just say it equals some algebra looking function, you know, x squared plus 7x minus 3, something like that. And g of x is a smaller function, times it by 4, you know, and then a little bit more, you know, just one more than that. So we can see how g goes. Like it goes, you'd square whatever your input is, you know, some input number, you take that, square it, times it by 7, you know, put stuff together, take the 3 out. Okay. Composition looks like this. And there's different ways to compose these together and all this stuff. So whatever, we'll just give you a basic idea. That's not a word. There we go. That's an I. Composition looks like well, here, I'll give you a little official notation. We say F compose G of X, then that's the way we say that. That's a weird little degree symbol looking thing. It's just not as high up as degree looking symbols are. But F compose G of X, is that how we say that? Or some people would say F of G of X. F of G of X is another perspective on the same idea. The way that's, I guess the idea here is what we're going to say is, okay, we know that my inputs go into the G function for, you know, G of X. And then whatever I get out of that, what we're saying here is whatever I get from G of X, I shoot into the F function, just like the rocks into chocolate machines going into the chocolate and gold machine. And so that's why we can also say it with this other notation. It maybe is a little bit more intuitive in that way. That's the, and then the input from that, or sorry, the output of that then becomes the input of the next machine, you know? That's what, this is how we write all that stuff. Maybe we don't need to get as far into all that, but there, oh, you know what, maybe we'll, here, save that in for on the side for a second. Maybe we'll just look at a very particular value that would highlight the idea. And so F compose G of X, let's put a particular X value in there. What if we said, let's figure out F compose G. We'll do, and so then it'd be, means I'm going to, whatever I get out of that output becomes the input into the second machine. And so let's see how that plays out. 2 goes into G, and then the answer from G of 2 goes into F. And here we go. 2 goes into G, looks like 2 going into a G function. So that's going to be 4 times 2 plus 1. So here we go. We'll start with first. Okay, first we'll have not F anything. We'll have G of 2 equals 4 times 2 plus 1. And then that's 8 plus 1 is 9 or whatever. So now what we've got is 2 was an input and 9 became the output, but that was just the first machine. This is turning rocks into chocolate. Now this chocolate, we're going to turn into gold by throwing it into the second machine. And that's what's going on here. But the 9 that came out is going to be the input into the second machine. So now we'll say, now let's do F of 9. Take the 9, shove it into the F function. Now the output from the first function, or the first machine, becomes the input of the next one. And so then we have 9 squared plus 7 times 9 minus 3, whatever in the world that is. That's 81 plus 63 minus 3. I'm getting like 141 in my head. I don't know, check that number, I guess. We'll just see. It's got to be around there. But anyway, this is the idea this would be what it would be like. This is what it's like. If we were to do it in these pieces like this is what it would be like if we were machines, one machine over to a second machine and do a second operation, and then I get the gold. Well, this outlines kind of the idea of how the machines are working together, but function composition at its best is when we tool one into the other. And so the quick way that you'll see this working out, and I'm going to make this brief, but the quick way you'll see this working out is if we say f composed g of x and we leave it in general terms without thinking about a particular number plugging into whatever, what that essentially means, guys, is that g of x, the function itself, since it's already a function of x and I'm already thinking x goes into g in general terms, I'll take that output, which is just 4x plus 1. I'll take the function itself and I'll shoot that into one big machine that just does the job of two. And the way that looks would be this, or I'll go ahead and write it on the side down here. It'd be like f composed g of x. The way that plays out is essentially x. And so I guess we could see that playing out up here. If I can see what g of x is, that's 4x plus 1. I'm going to shove that into the f function. Every time I see an x, I'm going to put 4x plus 1 instead. And so it'll be g inside of f. And so that's the way these things look. It'll be 4x plus 1 gets shoved into the f function. So that means when I see x squared, it's going to be 4x plus 1 squared. And 7 times 4x plus 1. Let's let that play out. 4x plus 1 squared plus 7 times 4x plus 1. Whoops. And then minus 3. In the end, what we see now is that this looks like the f function, but it ate the g function. And now we have g inside of f. And if I leave it like this, you can still kind of see that it's g inside of the f, because you can see the g function's inside there and it still looks like an f overall. Algebraically, what we do though, plus 1. I'm not going to probably do all the algebra, and then it'll be 7 times the 4x plus 1. We distribute that and minus the 3. By the time we FOIL all this out, what it ends up looking like is a single machine. Actually, who am I kidding? I'm going to go ahead and do it real quick. 4x plus 1 squared times another 4x plus 1. That'll be 16x squared plus, what's that? 4 and 4 is 8x. And then 7 times 4 plus 7 ends up looking like 16x squared. And then we have 8x plus 28x is something, 36x, I think. And then 1 plus 7 minus 3 would be like a plus 5. And by the time we get it here, here's why I brought this up. I don't normally like to do that many nuts and bolts on an intuition video, but by the time it gets here, notice how f composed g looks like just one machine now. This is just one machine that kind of looks like a beefed up version of the f function. This is one function that just takes your inputs, it squares them, times them by 16, times it by 36 again, adds them up and plus 5. That will spit out, it'll take the rocks, skip the chocolate, it'll take the rocks and spit out pure gold, all in one machine now. This is f composed g. It's two machines put into one, but by the time you see it simplified, it really is just acting as one machine now. And that's the idea behind composition or composing functions. Inverses of functions now. Part 2 is inverses of functions or inverse functions. The idea with those is, well, I guess the idea with those is to be backwardizing what a regular function does. We have inputs that become outputs, like rocks become chocolate. And so an inverse function would be the idea, and they became chocolate, through this machine. And I was like, but that chocolate was so bad. It was just discount store, nasty chocolate, that I was disappointed in. And the rock was really nice river rock, and I didn't want to get rid of it. And so I was like, can I get a different machine? If I can't run this one in reverse, you can't always unscramble the egg, If I had a different machine though, if I can't reverse this one, then can I make a new machine that makes these outputs now become the inputs, and that these inputs now become the outputs, where the inputs and the outputs have now switched, you know? And that's what inverse functions are all about, is it's a backwardizing function that undoes what the other function did. And so to get a quick example of what one, I guess G inverse of X, the way you'll see that written is they'll put a little -1 power looking thing up there. That's not to say you're exactly doing a -1 power of anything, although it's related to that idea. But the idea is, well, this is just us saying this is a backwards version of the G function. It's a new function. It's not G. It's a new function, looks like G, acts like G, but everything's backwards. It undoes what G did. This guy, G, is going to have inputs that give out outputs. And for G inverse, his outputs will be the inputs and vice versa. Well, like here, check this out. Notice. Let's go X, Y, input, output. If we said X input and we just plugged in some number, say 3 or whatever, then we notice that 4 times 3, our output would be 4 times 3, which is 12. The behavior of G. It's, it's the function we already knew. It's something that takes your inputs, it times them by 4, and then it does a little bit more than that. And so this is just a little bit more than 4 times as big as our input. 3 becomes a 13. You plugged in a 3, you got out a 13. So G inverse had better be a function that plugs in a 13 and gives you a 3 back, is the idea. And they tend to, at least in the beginning here, with the onset of these, the more elementary functions like linear ones and stuff, the inverses look like you would figure they would look to some degree. Like we have a +1 on here. To undo a +1, if I were to, we're trying to run the machine backwards here, or find a machine that runs the process backwards at least, we would say, well, to undo what this one did, well, a +1, I guess to take the 1 back off, you do some kind of a -1. So we'd expect G of X would have probably a -1 in it. It'll have some kind of an X because it's a function of X. So it'll have an X, it'll have some kind of a -1 thing going on. And then probably to undo a times by 4, we'd also have like a divide by 4 going on, some kind of a divide 4 action. And so, without knowing how to piece those all together, we at least know the idea is it'd be something to do with like, well, I have a -1 and I have a divide by 4. And I'm going to go ahead and undo. What did I just do? I can't see my drawing. There it is. Okay. Undo, 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 undo. There you go. All right. So, well, since I'm familiar with these, I guess that what you could say is, in the end, this one ends up looking like, well, if G of X had you, the story you tell is by order of operations or whatever, you times by 4, then you add the 1 on. Well, that means the 1, that was the last thing that got added on. So that's the first thing that needs to get taken off. And then you undo that times 4, and it'll be X minus 1, and then divide the 4. And this is, you don't feel like you have to be good at that right now or anything. That's a lot of what your homework is about. Is about halfway through your homework, you start working on how do I figure out what to do when, and how do I do an inverse. Don't feel like you got to know all that. But what we got going on is, since, I know these well enough to know that that'll be a good inverse, we're just going to test it and make sure that it does what it's supposed to. We're supposed to be able to plug in now a 13, and it better give me out a 3. So let's see if it works. If I shot a 13 in there, that'd be 13, and then take away 1. And 13 take away 1 is 12. And then, of course, 12 divided by that 4, well, that's 3. And it does what we wanted it to do. And that's what, I guess that's the best representation of inverse ideas and inverse functions I could think of for now. They have all kinds of applications everywhere. People think of cryptography, about the idea about like I'm writing secret messages. So every time I write, if I want to write the letter A, I'm really going to put a 1 or something, or I'll put a weird squiggly line, Well, in order for anybody to understand and decode or decrypt your writing, they're going to have to be able to say, well, every time I see the number 1, that means A, And so even just this idea about cryptanalysis, we call it, or, decryption, of deciphering these weird codes and ciphers. Well, that's a form of inverse functioning, for lack of a better way to say it, that's a form of finding inverses of functions. You have a function that encrypts a message and then a function that'll decrypt it, an inverse function. That's just one of a billion examples. Anyway, that's enough about inverses. And now we get on to the third subtopic, is we call it other. They don't put it in quotes, but I do, but whatever. Other algebraic functions. And let's talk about that for just a minute here. Other algebraic functions. Okay, so far, the functions that we've seen were in linear and quadratic, and then further into polynomial land, we were like, well, we've seen all these powers of x go on, f of x equals x to the 1, x to the 2, x to the 3, x to the 4, as far as you want to go. And then we've also seen, that's too many. And then we've also seen, like with rational functions, we mentioned the idea about, well, if you went past the 0 into the negative powers, x to the negative 1, x to the negative 2, etc., that brings us into rational functions. It's pretty much all the powers of x you could imagine. This is a 0, by the way. Except, what if we were to push just a little bit further? And this is about as far as we can go, and to close the gaps on, like, what in the world other powers of x could there even be? Well, what if we told you that, we have 2 and we have 3. Is there such a thing as x to the 2.5? What would that even look like? How do you interpret that if that's the case? This is what we're going to get into now, is this idea about the last of our algebraic functions. We're getting into these radical functions, we call them. And I'll show you what that looks like and stuff. Which is just intuition. So we're just getting some basic ideas down. But the idea is that, well, if there's any other powers left to cover of powers of x, it would have to come in the, it can't be that way and it can't be that way, because we've gone both directions as far as we can. We've even covered 0. It would have to be some weird fraction version. This would be x to the 2.5 or x to the 2.1 or x to the 5 halves would be a way to put that as a fraction. Whatever, all these things in between here. Are there powers of x that are in between these? And that's hard to wrap your mind around, because even just the idea about it, then you're saying it's like, well, I know what x to the 1 looks like. It looks like some number. X to the 2 looks like some number times the same thing. And here's x to the 3. Well, I don't know what it means to have 2.5 of it, because that's something. Same thing. It's not going to work. And so, especially when you put numbers there, it's not going to be like, well, this is 4 times 4, then times a half of a 4. It doesn't translate well into anything that makes sense to us. So let's talk about what this could possibly mean. And I wanted to notice something weird with me. First off, recall something. Or maybe you've never seen this before, but recall something with me about powers of things, of numbers. If I had something like 5 times, let's do 5 to the 3, and I times that with another 5 thing, 5 to the 4. And we're wondering, like, how does that go? And some of you guys might, if this is 5 to the 5 times 5 times 5, there's dot here. And then I have 5 to the 4, which is 5 times 5 times 5 times 5. Well, if I didn't put such a huge space between the dots, all we would see is a bunch of 5s timesing. So it looks like we have 3 of them here and 4 more of them, and all they're all doing is timesing. So what we can maybe say is, well, I guess this is 5 to the 7, right? Which kind of, it highlights a principle. Because what that means is, if 3 and 4 of them make 7 of them, that means really I could just plus those together, So I guess what we could say in shorthand is 5 to the 3 times 5 to the 4 ends up being 5 to the, don't times them, but 5 to the 3 plus 4, or 5 to 7. And that works for everything. Any old number to the 3 times any old number to the 4 equals that number, 7 of it, or 3 plus 4 of it. Anyway, okay. On that foundation, now that we have that, notice something with me. And this is really a recall also. Notice, okay, if we're to say, let's take the old square root thing back. Talking about square root of 9 equals, say, also negative, we've said. Not just because, but because, there's a reason. 3 times another 3, 2 of the same thing timesing is what makes that 9, or 3 squared makes 9, I guess you could say it as 3 squared or whatever. And so because of that, I call 3 a square root of 9. Okay. Something weird about this though. Okay, notice also though, just kind of keeping that in your mind. What if I took my 9 and I was like, I want to figure out, like, I don't, keep context here. We're trying to figure out what does it look like to have a power that's a fraction, and I was noticing something. To the 1/2 power. And this is what we're trying to figure out. Like, what the heck is that number? It's not 4.5, because remember, it's not a half or anything like that, or 9, half of 9 or anything. This is us saying, well, it's 9 zeros, like 1 or something, like this is less than 9 to the 1, but it's a power issue, 9 to the 2 is 9 times 9 times 9 times. And I'm like, well, what if you didn't even make it to one of them? 9 to the 1/2. Well, how much is that? Half would be maybe a good guess, but I don't think it ends up coming out that way, because there's something weird here I noticed. Check this out. Take our 9 to the 1/2, not knowing really what it is, but if we were just to investigate and say, well, let's play with this number and see if we can figure out what it is by the way it behaves, And I noticed something when I was playing with these. And I'm not the first to notice it or anything, don't get me wrong. I was just, this is my perspective on things. And so 9 to the 1/2, if I times that by another 9 to the 1/2, because we know the way that exponents work, that should be, since I'm timesing them, that means I should plus the exponents. This is 9 to the 1/2 plus another half. But you know what 2 halves adds up to? 2 halves is a whole, that the bottoms match. And so we do 1 plus 1 over 2. This is 9 to the 1, or 9 to the 2 over 2. This is 9 to the 1, which is just 9. That could mean a lot of things, but what I noticed that it means is that this means whatever 9 to the 1/2 power that you could take times the same thing and get a 9, which is 3 does. 3 is a number that you could take times the same thing and get a 9. Now we're saying that 9 to the 1/2 times that same thing gives you a 9. And that means to me that 9 to the 1/2 and 3 are both the same thing. So we start making these weird conclusions, and we're like, so I guess 9 to the 1/2, for one, I know what number it is. It is 3. Okay, so that sheds a little bit of light on it. But then also what we notice is, well, okay, 9 to the 1/2, if it's a 3, if it's the same thing as 3, and it behaves the same way as a 3, it has this property that square roots have. It has this property that when I take something times the same thing itself, I get 9. That means that 9 to the 1/2 is a square root of 9. So also we notice maybe a stronger result than that last one, is that 9 to the 1/2 is the same thing as the square root of 9, An idea about, well, what does it mean to have a fraction of a power? It means something about, some kind of a radical thing going on. And what you notice actually is, you might remember, guys, when we don't put a number here, like a third root or anything, it's a square root. Not be incidental there, And notice also there's a little 9 to the 1 inside. It's not like a bunch of 9s inside. So there's like our 1 and our 2. Further with these ideas, Anyway, so now we have this idea that a fraction power turns out to be some kind of a weird radical thing. And I won't do much more because, of course, we want to keep the video a little bit shorter. I guess we could demonstrate one more thing. If I said, well, here we'll start with 8 and we look for a cube root of 8. The 3 root of 8 is 2 because 2 times 2 times 2 equals 8, whoops, equals better looking 8. Well, like if I take 8 to the 1/3 power, oh, wow, let's work on penmanship here. 8 to the, knowing what that is, because we know what a half power is now, it's a square root, but a third power, this is another weird fraction, 1/3 power. Well, we notice that if I take one of those times it again times it again, well, that adds up to be, this is 8 to the 1/3 plus 1/3 plus 1/3, and that's 3/3, which is 1, or just that means 8 to the 1 is just 8. And so again, whatever this 8 to the 1/3 power is, it has the same property that 2 does. That, so meaning that it something, it has this power that when you cube it or take it times itself 3 of it, you get 8. So that means that 8 to the 1/3 is also a cube root of 8. And so now we have that 8 to the 1/3 actually means a 3 root of 8. And now we're starting to, okay, and it looked like square root of 9 is the same thing as, and we were like, oh, that's like a 2, in there. And we could even notice that that's 9 to the 1 inside. So we could put 8, 3 root is the same thing as 8 to the 1/3. And so X numbers up here and all the exponent numbers. And so we'll be like, oh, okay, 8 to this power, that root, 1 over 3 kind of thing going on, which is kind of cool because like powers and roots are kind of like stronger versions of times and divide anyway. And anyway, so this is what we noticed it looks like without going further. And we could go further with more demonstrations, but without going further into it, because this is a long enough video already, what we could say is it looks like in general, if I have some number, and we have to meet some stipulations here about not having negatives or how do we deal with negatives. But in general, without accounting for those weirdness things, we would say, well, it looks like if I have a fraction power, I know what it means. X to some a over b power. That's the same thing as taking your number and doing it to the a power, but then taking a root of it, or whatever. And so now we have we're run into a weird one, where we're like, well, clearly, 125 to, well, I know at least what it means. What they're asking for is this is a third root to the 4th. And interestingly, because we can do these operations in whichever order, I could take the third root of 125 first, which actually is just 5, and then do that to the 4th power. And that ends up being kind of a nice number itself. It's 625. So something that we didn't see coming was 125 to some weirdo bizarre power actually ends up being a nice number sometimes, They don't always, most of the time they're nasty, I guess. But anyway, maybe that's enough for now. And then what we've noticed is that we closed in all the gaps. Now we have, with this, the last of our algebraic functions, we call them radical functions. We have now figured out, how do I find out powers in between 0 and 1 and 1 and 2? Well, powers that are fractions. And what that does for us is it means we've covered the whole stinking number line of powers of x's. Nowhere else to go. Powers of x's. And so now, now we become on this new adventure as we get into modules 6. Where, are there more ideas out there? There's x to other powers, or is there some whole other thing to think about? There's where we get outside of the world of algebraic functions. This closes out everything we needed to say about algebraic functions, because we found positive powers, zero power, negative powers, weird in between powers now. We got it all. All right, that's all I got to say.